In this video, you'll learn how to train a computer vision model in LandingLens for Snowflake. Specifically, you'll learn how to train a binary classification model using both fast training and custom training, how to configure splits, and how to queue multiple training jobs. Here we go. I'm working in LandingLens for Snowflake, and I'm inside a project named Pneumonia with uploaded labeled images. In a previous video, we uploaded all these images via a Snowflake internal stage and inspected that the labels and classes had transferred correctly. There are 50 normal chest x-rays and 50 that have pneumonia present. Note in the two lower charts that all the images are unassigned to a split, also known as a partition. Now it's time for modeling. On the Build tab, you can access the fast training by simply clicking the blue Train button. How easy was that? During fast training, LandingLens automatically fine-tunes its settings to optimize model training speed. LandingLens performs the following series of steps when training a model. 1. Preparing a data snapshot. 2. Provisioning a GPU. 3. The actual training and learning. And 4. Calculating performance. Since I'm using LandingLens for Snowflake, which is offered as a Snowflake native app, the GPU is provided by Snowpark Container Services. To manage costs, the GPU is set to auto-suspend and auto-resume. Be prepared to wait up to 15 minutes for the training job to actually start if the GPU needs to start up first. During the model training process, you can view the loss chart and training information by clicking the View Details button on the model tile. Lower is better on the loss chart. Loss is a measure of model error. As the model improves during the training process, the line goes down towards 0 over time. Note that the loss chart is calculated on the train split. When using the fast training option, LandingLens applies machine learning best practices to do the data partitioning into train and development sets for you behind the scenes. Let's give this training run a more descriptive name, such as fast training, and move on to set up custom training. First, to emphasize that images have been assigned to train and dev splits during the fast training, I'll click on the histogram next to the image count. Now you see that images are assigned to train or dev. Any future training jobs will use this same split unless you intentionally change it. Let's do that now. From the Select menu, I'll choose Select All. When images are selected, the Options menu appears at the bottom of the screen. I'll select Set Split and then the radio button next to Unassigned. With all my images unassigned, I'll navigate to the Split Management interface by selecting Auto Split from the 3 dots button. Here, I can manually select my train, dev, and test percentages. I can choose to adjust values for all classes together or separately to achieve the split I want. Let's over-index on normal images in the dev and test splits. Note that the test set is not required and you can set this to 0. I'll click Assign Split at the bottom. Now I'm ready to configure custom training. I'll click the blue arrow next to the Train button and select Custom Training. Step 1 is setting up the data. The split shown here matches the work I just did. Note that basic splitting can be done from this interface, but the prior one offers more user controls. Clicking Next displays Part 2, Configuring the Model. Note that you can configure multiple models at once by clicking Add Another Model. Let's configure 3 experiments with slight differences. I'll call them Experiment A, Experiment B, and Experiment C. For Experiment A, I'll accept the defaults. These defaults do differ from the fast training defaults. For Experiment B, I'll modify the model size by selecting the 16 million parameter version of ConvNext. For Experiment C, I'll modify the augmentations used. Since we're working with chest x-rays, I'll remove the horizontal flip, which would place the heart on the opposite side of the image. I'll also remove random augmentations in favor of selecting my own. Clicking plus brings up the list of available augmentations. I'll select random brightness and preview its effect on a few images. Then I'll select random rotate and reduce the angle of rotation to be -10 to +10 degrees. The preview looks good, so I'll click Add. Many of the other augmentations are not relevant to this use case because I would expect the X-ray technician to reject any blurry images and have the patient hold still for another. This is an example of applying subject matter expertise in designing your training jobs. When I click Train, my jobs will be added to a queue. You can queue multiple training jobs, and LandingLens on Snowflake will process them sequentially. To get information about the number of jobs in the queue, hover over the Provision GPU step to bring up a tooltip. The job count includes training jobs from all projects and all users in your instance of LandingLens on Snowflake. Click on View Details in the model card to monitor the training progress and observe the loss over time. Experiment B is pretty close to finishing. Clicking on the Models tab brings up a summary table for my 4 training jobs. Now I can work on other tasks while my models finish training. The exact duration depends on many factors, such as image size, number of epochs, number of classes to predict, etc. Since fast training is optimized for speed, it's a nice way to quickly determine if you've framed your use case correctly and if it appears solvable. Let's let these finish and pick it up in the next video, where we'll evaluate the absolute and relative performance of these 4 models. To recap, in this video, you learned how to train a computer vision model in LandingLens for Snowflake. You learned how to use both the fast training and custom training options, how to control the splitting of your data, and how to queue multiple training jobs.